In this video, we want to talk about the recently published paper from Meta called MEGABYTE, predicting million-byte sequences with multiscale transformers. In discussion of autoregressive transformers, which are related to things such as ChatGPT, one particular limitation is that when it comes to long sequences, they scale poorly. For example, they are able to generate, let's say, 500-word responses such as those that ChatGPT does perfectly, but when it comes to longer things, for example, if you want to read a book, podcasts, codes, high-resolution images, and things like that, they are going to be limited. Now, this paper, specifically MEGABYTE, is focused on basically enabling end-to-end and differentiable modeling of sequences over 1 million bytes. That's why they call it MEGABYTE. They do it by proposing a hierarchical system in which you have a local submodel and a global model. They segment these long sequences into patches, and then they use a local submodel within these patches to encode them, and then they also have a global model that works to do the representation learning this time between the patches. They empirically validate this model and show that it results in great performance in different benchmarks. So without further ado, let's get to it. They start the paper by talking about large language models and one of their major limitations, which is the limited context length in many of the transformer-based models. As they mention here, large transformer decoders typically only use several thousand tokens of context. The components that are critical in analyzing the time complexity of running these types of models are quadratic cost of the self-attention being one of the major components of the transformer, and also, more importantly, the cost of large feed-forward networks that are applied per position. Now, this paper, namely MEGABYTE, is trying to offer an alternative to this kind of usual tokenizations that have been happening, while seamlessly allowing modeling long byte sequences, in other words, long sequences of data. Now, this model, MEGABYTE, is composed of three major components. One of them is a patch embedder. So basically, roughly speaking, the idea is that you have a long sequence, you want to break it down into patches, and you want to use a model to basically represent these patches as embeddings. You want to concatenate these embeddings and have it as a representation of the patch, and then you want to have another model, let's say the global model, running on these patch embeddings in order to learn the representations for the system. And they also want to do this kind of unsupervised task of utilizing the global context and also the local representations of an embedding in the task of predicting, let's say, the next byte. So this is overly an overview and summary of this work. Nonetheless, this work is composed of three major components: a patch embedding, a global module which runs on the patch embeddings, and a local module which is byte level and it's supposed to generate representations for those bytes. One observation that they have, which is essentially one of the motivations of this work, is that they mention in this part, we observed that for many tasks, most byte predictions are relatively easy. And they mention the example of completing a word given the first few characters. Now, with this example being said, what they conclude is that large networks per byte are not necessarily, necessary or required, because much smaller model can kind of use this for the intra-patch modeling, namely bytes within a patch. All in all, their contribution is the MEGABYTE architecture with three major improvements. One being the subquadratic attention. Given that you have a long sequence of bytes, you break it down into patches, and then you have a sequence of patches. So you have the sequence of bytes within a patch and patches within a sequence. Therefore, you have two shorter sequences rather than a long one. And they mentioned that given the optimal patch size, the self-attention cost will be reduced to this subquadratic ON to the power of 4 divided by 3, which is tractable even for long sequences. So this is the first major contribution of MEGABYTE. The second one has to do with the cost associated with the feed-forward, with the per-position feed-forward applications in the original transformer models. And it was observed that more than 98% of the floating point operations that were happening in a transformer were actually being happened in the position-wise feed-forward layers. Now, in the MEGABYTE, you could consider that the patch's representation is going to be sort of a concatenation of the bytes within a patch, and then they will be concatenated to generate the patch representations. So what they do is that they have a large feed-forward layer per patch rather than per position, and therefore they can work with larger and more expressive models with the same cost. For example, say a patch size is P. namely you have p bytes that are represented within a patch. If you use a baseline transformer, you're going to have to run a feed-forward layer on each one of these tokens. Namely, you have to have m parameters, which is your, let's say, linear. You have to run it p times. Now, in the megabyte, given that you work with a patch embedding, of course, you have like, p elements in some sense, but you have one feed forward applied on all of the representation because you consider the patch as a single element of a, let's say, a higher level sequence of sequential representation of your original sequence. Therefore, you have a layer that this time it's a single layer, but it has MP parameters, so you run it once for the same cost. And lastly, they have the parallelization in decoding. In the general autoregressive transformers, you're going to have to do the computation serially when you're doing the decoding, because in each time step, the output is going to basically be from the previous time steps. Now, in this context, they generate representations for patches in parallel. Now, megabyte is going to allow greater parallelism, which happens during the generation, resulting in 40% faster than a standard 350 million transformer while having 1.5 billion parameters. It is important to mention again that the two main goals of the megabyte architecture is to kind of overcome the context length limitations of the baseline transformers and allow training much larger models, and also have important performance improvements so that they perform also parallel and maybe better than many of the similar transformer-based baselines. It provides an alternative to the well-known tokenization, which, as they mention here, tokenization complicates pre-processing and multimodal modeling and also transferring to different domains. And instead, in megabyte paper, they focus on the lowest level of representation of these sequences, which in this case will be the bytes, and they focus on that. Therefore, it is transferable in some sense between different modalities, which resulting in the megabyte models, which they mention here, that it performs well across different domains. It is important to mention that megabyte transformer is a autoregressive model. However, it does allow better parallelization in decoding, as we will discuss later on. Consider the byte level representation of your sequence, which could be a sequence of bytes, let's say 0, 1, all the way to t being the number of bytes in the sequence representing your input and your observation. So this would be the sequence that megabytes work with as its primary input. Each one of these x's is going to be represented as a byte. Now the goal is to break down this sequence into kind of like a hierarchical way into patches, and then from patches to the representation of the sequence. Now you're going to have an embedding for each one of these bytes. That embedding would be of dimension d of g. By the way, this g is not multiplied by the d of g. Let me actually write it again. It's d of g, like here. So d of g would be the length, the dimension for the embedding of the bytes, and p would be the number of bytes per patch. Therefore, the representation for the patch would be the concatenated representation of its bytes, and therefore it will be of dimensions p times dg. Now for each byte, you have a global embedding. So this global embedding of xt means this. You have a global embedding table for byte representations, for example, implemented using torch.nn.embedding. So the fact that it is global means that this is the embedding that is going to be used in order to embed the bytes in order to be fed as the input to the global model that works with patches, okay? So this is the global embedding. And then for the byte, for each one of the bytes, so let's say you're looking at position t in your sequence, and let's say its byte is all 0, 1, something like that. So this is going to be corresponding to a specific embedding. So this would be the embedding for position t. What this means here, the reason why we have xt here in index and t here as index, is that this embedding relates only to the content of the byte, not the position, but this result would be basically for the position. So for example, if you have a byte in position 1 and position 10, you're going to have the same content for edge of 1 and edge of 10. So this is what this means. Therefore, these E's in this paper are lookup tables for byte encoding. So these are trainable embeddings. Now, in addition, you also have a positional embedding. This time, this embedding is going to focus only on the position. Now, global model comes into the view. Note that global model in the context of megabyte paper is patch level, so it's not byte level, it's patch level, and it works on patch level representations. So the input for the global embedding, or for the global model, is going to be composed of k, let's say your sequence length of k patch representations. So imagine you've broken down your sequence into a sequence of patches. You will have k patches. In each patch you have p bytes, and each byte is represented by dg. So this global input is going to be a representation of patches, because let's say the global would be a transformer and the input is going to be the patch representations. So you have a sequence of k patch representations, and each representation being the concatenated embeddings of each bytes in the patch, so it will be of dimensions p times dg. In addition to that, you're going to have to do some sort of a prefix tuning of sorts. What that means is that you also have a global padding, which is a trainable embedding, and when you have created this input for the global model, you basically pad or kind of append this, or in some sense prepend this global pad to the beginning of your sequence. So this is going to be a trainable set of inputs, global pad. So if k is equal to 0, let's say k being the new index for your input to the global model. If k is 0, you have this trainable starting of the sequence, and if k is 1 to k, you will pick the previous patch representations. This input is also of dimensions p times dg. Now let's talk a little bit more about the global model. The global model is going to be a decoder-only transformer. The model dimension, or the basically element dimension, is going to be p times dg because it's patch level resolution. It's going to do self-attention and also causal masking. So you have the global input, which is from 0 to k, 0 let's say being your global pad, the E global pad. So you have k plus 1 patches being fed to this global input, and then you're going to get the output representations that basically attended to everything and has seen sort of a high-level representation of everything in your sequence in some sense. Now you want to project them to now go on a local level. So one thing about megabyte paper is, just to kind of keep in touch, is that you sort of go from global to local in some sense, which is kind of not super familiar, because in many of the papers that do something hierarchical, you go from local to global, but it's just something that I wanted to note. So you have this, let's say, W or omega of GL, meaning global to local projection. So the dimension of this is going to be dg times dl. What this essentially means is that you have the patch representations that are generated by the transformer. Their dimensions are p times dg. So for each embedding that you have fed to the transformer in part of your positions to the global model, so global model is a transformer, you fed it the representation of the patches, it has gotten those representations, it has embedded them into, again, p times dg dimensional representations for those patches. Now the goal here is that at that point you're going to unfold them again, and then you are still going to work with p dg dimensional embeddings. So you got each one of your outputs of the global transformer being a p times dg dimensional output. However, you unfold them and you get p dg dimensional elements. Okay. Now with those, you're going to use this global to local to map that dg dimension to dl and now go to the local model. So you're going to have your local embedding. This is going to be byte embeddings for the next patch. All right, so the input for the local model. If p is 0, you're going to have the local padding. It's kind of similar to what we had as a padding for the global model. And if something else, you're going to use another byte embedding table. This time, this one is going to be used effectively for the local model. So it's similar to the global embed, it's just that it's a different embedding codebook. Now, this is going to be the addition, this is going to be something additive that you will add to the representations. As a base, also, you have the global output, and then you project it to the local model using this WGL. So you take the outputs of the global model and you project it and you add this component to it. Now you feed it to the transformer for the local model and you get the outputs. So if you look at the byte position t in your sequence, you have k times p plus p. This p is uppercase p, this is lowercase p. What this means is that you are looking at the pth element of the kth patch. Now you can use the table of the byte embeddings that you're using for the local model, and you can use its, let's say, dot product similarities with this local output representations, let's say the k and pth, okay, and if you do this and you do the softmax, what you're going to get is going to be the probability layout over the byte xt given x0 to xt. So in a causal way, you're looking at the probability layout predicted by the local model. Now let's go over a visual representation of what happens again. You have a sequence of your input being a sequence of bytes, so this could you use to represent, let's say, audio or any other types of sequence, anything that can be represented with bytes, which could be, anything. You're going to look at bytes of the sequence, so these are going to be kind of like minimal chunks of this representational information for this sequence. You're going to take each byte, use the lookup table for the global model, and represent that byte, and add the representation of the content of that byte to the representation of the position of that byte within that sequence, and you're going to end up with a byte embedding, which is going to be fed to the global transformer. All right, with that representation, you're going to have a DJ-dimensional representation of each byte across the t bytes that comprise your sequence. You're going to add this trainable global padding to it, which is basically a kind of like a trainable patch. So it has p DJ-dimensional elements. All of this matrix is going to be trainable. Now you're going to take this new sequence and you're going to feed it to the global transformer, which as a result is going to generate patch representations for the k patches of your data. And each patch representation is going to be of dimensions p times dg. You're going to unfold them and get p dg-dimensional representations, because now you're going to go back to sort of byte level representations. You're going to project them to dl from dg in order to use them in the local model. And in order to create this, you use the local embedding of those bytes and also use the projected version of the outputs of the global model. Let's look at this again to better understand what's going on. You're going to have a sequence of patches that are going to be processed by the global model. Remember that you also had a single embedding patch, the trainable sort of prefix thing that you added, so it offsets everything by 1. And now you have the embedding representations for each one of the patches from your global model, and you kind of unfold this and then project it, so you have DL dimensional representations for each byte in your patches as you go forward. Now the goal is essentially predicting the bytes in the next patch in some sense. In order to do this, first you add this DL dimensional padding to the beginning of the sequence for this next patch. Remember, you want to do the predictions in this next patch thing. And let's say, for example, you want to predict this one. You add this padding to here, and now you have the representations of the previous patch as the outputs of your global model. So if you look at figure 2, you see this equation which says that the input to the basically local model for patch k and the byte, the index of byte within the patch p, and ignore, for example, let's say p is not 0, you're going to have the projected version of the global output at position k, which is basically the pth dg fraction of it, the pth dg portion of it, plus this local embedding, which is the lookup table for byte embedding for the local model at position k, the patch k is p minus 1, meaning the pth position of patch k. So what this kind of says here is that due to that offset for the the embedding patch, the trainable patch that you had at the beginning of the patch sequence that you were feeding to the global model, you're essentially going to have the outputs of the global model for the previous patch added to the initial embedding of the bytes in your current patch on which you want to make the predictions. Once you add them in, you will have this local input, which is going to be fed to the transformer local, giving you the outputs of the local model. And you also had the embeddings for the local model, namely the representations for bytes that is being used for the local model. So you could kind of get the dot product of them, you could get the softmax of them at position p here, and say that you have t being the position k times p plus p. And now if you apply this, you have a probability layout over possible byte values. So if you want to see what is the probability that the value of the byte at position t is xt, this term over here is going to give you the probability distribution of the tth position having the byte value xt given the byte values of 0 all the way to t position. And this sums it all up as to what the megabyte model is doing. Motivated by certain observations, they also try out several variations of this model as well. The first one being augmenting the megabyte architecture with a convolutional patch encoder. Now, the reason why they introduced this is that in what was discussed as the megabyte architecture, one problem is that when you're looking at the byte sequences might receive different representation depending on where they are located within your sequence. For example, the model might need to learn the meaning of a word at different offsets of your sequence. To alleviate this impact, they also tried augmenting the system with a patch embedder with a causal convolution layer, and therefore achieving a translation invariant contextual representation of the sequence. So in some sense, they represent the bytes before they are being chunked into patches. They try filter sizes of 3, 5, and 7. The other thing they try is a cross-patch attention. One other thing is they try in basically the local model that was being used for those byte predictions. They also try kind of conditioning it in addition to the R elements from the previous patch as well and kind of increasing the context length of it. Lastly, they try strided inference. They realize that the per token loss in each one of the patches is going to increase towards the end of the patch. The reason why for this is that at the beginning of the patch, they're going to rely on the global model, which is better trained and has more semantically interpretable representations. But at the end of the patch, it's going to rely more on the local model, which in their words is weaker. Therefore, they propose the alternative method of strided inference, in which for each sequence, they have 2 forward passes. One of the inputs is offset by p divided by 2 positions from the other, and therefore they combine it to kind of predict the complete sequences, and they show that this approach improves the result. One of the things that they mention is that many of the improvements that Megabyte offers can be achieved with the global model alone. Now, the global model in this setting would resemble something kind of like a decoder version of the visual transformer. However, the issue is this. Let's say you look at the byte values from position 0 to the tth byte, and you are looking at the joint distribution for the next patch. Now, this is essentially what the global model in the context of Megabyte paper is concerned with. Now, given that each patch is composed of p bytes and each byte is a 8-bit number which could have values from 0 to 256, you will have 256 to the power of p possible options for your output. Given that you have this many different outputs, yet you need to kind of look at the probability layout of each. Now, if you directly try to model this, the value of p should be small, because if you increase the values of p, it means you're exponentially making the task more complicated, given that you have 256 to the power of p possible options for the output. Now, this is not ideal. Now, one thing you can do to circumvent that is to kind of break it down into individual conditionally independent distributions. So this distribution would be p of xt plus 1 given this, xt plus p of this, and then the problem with that is that it kind of breaks it down into character level. So if you have, for example, words such as cat and dog and things like that, you cannot kind of do like okay, this is going to be a patch which is 50% cat or 50% dog, something like that. Instead, you're going to have to look at the byte level, or the byte level representations. Namely, you will have probabilities for CAG and DOT, given that you are looking at the probability of this part of the sequence, this part of, and this part of. So the fact that they have a local model instead in their autoregressive setup and conditioning on the previous characters, it sort of allows it to only assign probability to the strings that would make sense, or in other words, the desired ones. The next component is increasing parameters for fixed compute. By doing this hierarchical setup, Megabyte allows larger model for the same cost, given that you have made the self-attention sub-quadratic in terms of the length of the input, and therefore also used the large feed-forward layers across patches this time, rather than individual tokens, and therefore you have the fixed compute, but you also have increased the number of parameters. What does it mean? It means that, let's say previously you had a let's say m parameters in your feedforward layer, which was applied on each token. So you had m parameters that you were training, you were applying it p times, so in terms of computation you have m times p. In this case you have m times p parameters, meaning larger parameter, more complex model that has higher learning capacity, and when you apply it you'll still have the amp cost, so you have higher number of parameters but the same cost for propagating information. The next component is a reuse of established components. So the megabyte architecture has two transformer models, and they're interleaved. You have shifting, reshaping, and linear projection. So you're reusing the established components, and it increases the likelihood, they mention, that this kind of architecture is going to inherit the desirable scaling properties that transformers have exhibited so far. Next part is talking about efficiency analysis, which is the section number 3 in this paper. Let's just start with the training efficiency. The first module that we have to focus on is the attention module. Now, when you look at the transformer architecture, you have a sequence of length t. You're going to look at the kind of the similarity between each one of the tokens and each one of the tokens, so you have O of t2 complexity. And there have been a large number of works focusing on kind of reducing this. There are sparse transformers, routing transformers, and things like that, kind of bringing this complexity to t3 divided by 2. Now, in the case of megabyte, you have a sequence length of t bytes, you have a patch size of p, therefore the global model is going to have a length of p divided by t, which therefore means that you have the order of t divided by p squared number of operations. Note that this is for the global model. Now, let's go to the local model. You have p divided by t sequences of length t. I think it has to be t divided by p. But again, so you have t divided by p times p2. Okay, this is going to be the order of complexity for the local model. Therefore, you have t divided by p squared plus tp. And if you set p equal to the t to the power of 1/3, the complexity is going to be of order of t to the power of 4/3, which is subquadratic and manageable even for very long t. As for the feed-forward layer, so in the megabyte you have two transformers. You have global model, let's say you have mg parameters on a sequence of length t divided by p. You have a local model with ml parameters, and you have t divided by p sequences of length p. And then in terms of estimate, you have 2 times t times mg divided by p plus ml floating point operations. Let's look at this formula again. So ml is the number of parameters in the feed forward for the local model, mg is for the global model. Now the thing is, for the global model, you look at t divided by p number of elements, okay? And then for the local model, you have t elements. Now let's say the mg, or the number of parameters in the feed forward of the global model, which is more complex, is a lot larger than ml. So this thing is going to be reduced to 2 times t times mg divided by p, which means that the use of patches in this case is going to allow a feed-forward model that is p times larger than the one in the original baseline transformer with the equivalent number of floating point operations, which is definitely an improvement. They evaluate this and, for example, showed that if you have a megabyte, okay, with the patch size of 8, it's going to use less floating point operations than transformers or linear transformers. More details are available in this part, which is section 3.1 of the paper. Then there's the generation efficiency. So the original autoregressive nature of the autoregressive transformers, the decoder-only transformers, is going to make generating longer sequences slow. Now, when you have the megabyte architecture, you have the L global layers in the global model and L local layers in the local model. Let's say you have patch size P. You have L local plus L global layers for generating the representations, and the generation of each patch is going to require a sequence of number of global layers plus P times local serial operations. Now, given that the global model has many more layers than the local model, and with this kind of like additive kind of capacity for parallelization, megabyte can reduce the inference costs by a factor close to P. The rest of the paper delineates upon utilizing the megabyte architecture across different domains of analysis, one being image modeling, the other one being language modeling, and finally audio modeling. And they basically pick certain benchmarks, they compare it against the perceiver AR, and baseline transformer. In some of the cases, for example, in image modeling and applying it on higher resolution data, they, for example, mentioned that perceiver, AR, or transformer are not able to handle any sort of super long sequence lengths. So for those things are a bit different. One thing they do is that they try to kind of adjust the hyperparameters in a set that across these three model families and model architectures, the amount of time it takes for the byte prediction in forward pass to be kind of the same. Therefore, in terms of the computational budget, you are looking at models that kind of, in some sense, cost relatively the same. So, for example, this table right here, table number 2, is the bits per byte measure for the megabyte perceiver AR and baseline transformer model on these different text datasets, arXiv code, books, stories, and PG19. It shows that megabyte consistently outperforms them and results in lower entropy in the outputs. You can see like the detail of the length of these, or in some sense the size of these datasets in this table, table number 1. They also went ahead and looked at the PG19 dataset. They kind of broke it down from bits per bytes to word level perplexities and showed that the state of the art is this paper, which achieves 26.5 megabyte. Even in this compute match setup with these three, achieves 36.4, a result which is competitive with the state-of-the-art models that are trained on the subwords. You can look at the other tables and see that, for example, for the ImageNet 64, and in ImageNet also megabyte achieves kind of consistently outperforms the other models. In the audio modeling as well, they showed that the megabyte model achieves much lower results than the results of the perceiver AR and vanilla transformer. Therefore, it's great for audio modeling as well. Now, the paper is going to have a lot more details on certain aspects of the training and outputs and certain ablation studies, so I really encourage you to read it. All in all, this paper was really interesting to me, and therefore I just wanted to discuss it with you. Thank you so much for watching this video.